value problem. So you kind of read at the top there, bigger so you guys can read it. It's problems where integration is used to find the original function. Or if I want you to find like an initial position where I give you a velocity and an acceleration, it's just basically working backwards. All right, what's our initial function? And when you hear the words differential equation, a differential equation is any equation that represents a derivative. So if you look at this equation right here, you'll see the equal sign, hence an equation. The fact that this is a derivative means it's a differential equation. Solving a differential equation, if necessary, you're going to separate the variables. That won't always be necessary, but that is something that we would need to do. Once they're separated, you're going to integrate the two sides, so find the antiderivative of both sides. And then now for the first time, this is the only real extra step. We're going to solve for C. So we've been saying we don't know what C is. And what we did previously, we don't have enough information to solve for C. But the information you're going to get today will allow us to figure out what our C is. Okay? So with that, start out. You'll find this, at least the first page is pretty nice. If I tell you to now solve this equation, so it says solve for y, given the fact that you're at your derivative. So we would know if I'm at my derivative and I want the original y equation, we need to do the antiderivative of this. But if you notice, number one here, where it says separate the variables, what that refers to is the idea, we kind of talked about this a little bit with, we call them differentials. We want to get this dx, we want to multiply both sides by dx so that the only thing we have left over on the left-hand side is a dy. And then you'd have to do the same thing on the other side so that we actually have, if you've done the homework, if you've looked at the homework, we always have our function multiplied by the change in x. Just when we did our Riemann sum, it's always the function times our change in x. So we need to create that. So on the left, our function is really just a 1 dy, and on the right-hand side, you get the 3x plus 5 and then the dx. So that's what it's referring to here when we say separate our variables. Once that is done, then we can go ahead and find the antiderivative of both sides. So you're going to put that indefinite integral in front of both of those. Let's do the right-hand side first. So the antiderivative of this is 3x squared over 2 plus a 5x and then plus our constant. What we now have though is a right-hand side. Okay, notice again, this is an equation, so we now do have this over here. So what we are looking for is the antiderivative of 1. But you have to understand now, we are doing 1 times the change in y. So we're doing this now with respect to the variable y. So on the left-hand side, the antiderivative of 1 dy would just be y. Thursday, Friday, you would have stopped there. That's as far as we would have gone. But what you're now going to see is an extra piece of information that you did not have last week when we were doing these, and that is a point that we know lies on the original curve. So if I know that point lies on the curve, then I can go ahead and let my y be a 6. Let your x's be 0. So then this term is a 0, this term is a 0, and all we are left with on the right-hand side is your c. So what we find out pretty quickly is that c is equal to a 6. And if we now know that c is a 6, I can now write this original equation and no longer have to worry about this, the generic plus the constant of integration that we don't know, because we now know it. If we go through the point 0, 6, then our c would have had to have been 6. And then that's it. So that's what I'm saying, there's one extra step with most of these anyway. Okay? And right now you're thinking, that's not too bad, I hope. Number 2, if I tell you that y equals f of x is the solution, so here's f of x, here's our derivative to this differential equation, find the solution if f of pi is equal to a 3. So same process. We don't have to worry about the separating of the variables. We really only need to worry about that when it's in this fraction notation. So when it looks like this, we are ready to do our antiderivative right away. The antiderivative of f prime, we can just call f of x. I also like making you do that homework assignment, just to make sure we keep all of our positives and negatives straight when we're doing these. The antiderivative of sine should be a negative cosine. The antiderivative of a negative cosine should be a negative sine, and then we know we get our constant. But if we now know that the point, let's write this as a point, just to make sure we understand what this means. This is the point pi, comma, 3. If we know the original graph has to go through that point, that now allows us to do some substitutions to figure out what our c is. So we're going to let our y coordinate, so the f of x be the 3. Let your x's be pi's. And then now we can solve that equation for c. So pi on the unit circle is over here. So when we want a negative and then we want the cosine of pi, that's the negative, or the x coordinate over here at pi, so that should be the -1. Minus the y coordinate over here, which is going to be a 0. So this c, if I can squeeze it in there, should equal 2. The c is not your answer, so don't just find c and then leave that as our answer. Our final answer would be this equation here, just now rewritten instead of the generic plus c. Uh-oh, I might run out of room here. Plus 2. Hopefully you can see that good enough. All right. And that's it. Now, the next couple we use fancier words, but it's largely the same exact thing. So this one's now, I'm telling you, given the velocity, so I'm giving you this as a velocity equation, and an initial position. So this is just saying at the time of 0, my position would have been 10 meters, feet, whatever our unit would have been. Find the body's position at any time t. So we would hopefully understand the whole position, velocity, acceleration idea. If we are currently at a velocity and I want you to find the position, we've got to go up one step. So we do that with our antiderivative. The way you're going to now call the left-hand side, this is important because this is not a free response question, so I would grade this the exact same way. We don't want to call this like P of t unless there is no name for the position function. You are told right here that our position function is the function s. So when we do the antiderivative of v of t, the way that that was written means our position function is going to be called s of t. We do the power rule over here. So we do the t squared, divide by the 2, add your constant. So simplified, that's 4.9 t squared plus the c. And then really simple here, this is telling us if we let our time be a 0, so then this whole term is going to 0 out. At the time of 0, we knew our position was 10. So then we can go ahead and write this equation. My position at any time, which is what the answer to the question is asking you for, is 4.9 t squared plus a 10. So again, pretty simple stuff, hopefully. Now, 14, there's a little typo I'm going to have you change, but big picture stuff I think you'll understand. This is now a of t, so this is now going to be giving us our acceleration. And then the little typo you want to change, these should be t's. This should be written in terms of the variable t. So our acceleration at any time is defined by the difference between cosine and sine. We want to now find, ultimately, the answer to the question is the position. And then what you were told is at the time of 0, our velocity is 2. And at the time of 0, our position was 0. So again, understanding how these guys are all interrelated here. Now you're actually starting at the bottom, and we've got to find a position. So we're going to have to knock 2 of these out. So when we do the first one, we would know the antiderivative of acceleration you would call velocity. Do cosine and negative sine real quick. Just make sure we keep the positives and negatives straight. All right, and Ryan, what do you got there, Ryan? Positive or negative sine here? Good. So positive sine of t, and then what? Good. So both of those should end up being positive. Positive sine, positive cosine. Now, we do need to, so don't write this down yet. We do have to find the antiderivative one more time because we ultimately want the position, but we don't want to do that until we know what this constant is. All right, so we want to figure that out first. So don't, even though we know we have to do one more antiderivative, we don't want to do that just yet. We want to now use this information that at the time of 0, our velocity was 2. So now we do that substitution. Let your velocity be 2 when the time is 0. Like we did in the previous three problems, now we can figure out what our c is. So the sine of 0 is 0, but the cosine of 0 will give us a 1. So the c in our velocity ends up being a positive 1. So off to the right of that one, I'm going to now rewrite my velocity equation in its entirety. And it should now be sine of t plus cosine of t. And we now know our c is a 1. All right, antiderivative. The antiderivative of velocity is going to give us our position function. But if you now look at how I have this written, I am saying that our position function is x of t. All right, that's probably our most common because we do a lot of horizontal motion along the x-axis, so it's our x position at any time. So when we do the antiderivative, this is telling us to call this position function x of t. All right, then one more time, do that antiderivative. All right, and this one, Aaron, what did you get for these two guys, sine and cosine? Good. So negative cosine of t, and then a positive sine of t, and then plus, I'm sure nobody out there put an x, right? You're not going to put x for the antiderivative of 1, are we? Because what variable are we dealing with in this case? T's, right? So make sure this is a plus t, and then plus our constant. So don't throw an x down. And then finally, to figure out that c, we now use this entire piece of information here, that at the time of 0, our position is 0. So you let all the variables become a 0. So a lot of zeros, but it doesn't zero out. You should get that c to end up being a positive 1. And then because I'm lazy and I'm the teacher, I don't have to. You don't get to do this, but this ends up being our answer right here. All we now do is go back to whatever this c was, and we replace it with what we now know it to be. And then that c is a 1. Right? Simple enough, hopefully. The next few, though, tend to get a little bit more interesting. 5, first and foremost, this is the first one since number 1, where we have the fraction notation, dv over dt. So the whole idea that first and foremost you have to separate your variables pops up in this one. So we do want to do that. So in this case, what you're going to do is multiply both sides by the dt. And then on the other side, way over here, you're going to multiply that by dt also. So for secant t tangent t. I always get told my t's and pluses look a lot alike, and now they really do writing with this thing. But that's what we get initially when we separate our variables. Then you were told that at the time of 0, our velocity is 5. The reason that is important, really understand what this is. Isn't this a change in velocity over a change in time? And isn't change in velocity over change in time, isn't this really just a different way of expressing an acceleration, change in velocity with respect to time? So that's why when we do this antiderivative, what we're really doing the antiderivative of is an acceleration, and that's why when we do the antiderivative of 1 dv, you're going to get the variable v. And then I'm going to go ahead and put it as v of t. It's our velocity with respect to time. If you don't have the of t part, that's not wrong. So if you just put a v, totally fine. Do that antiderivative real quick. And what tends to cause a little bit of an issue is this guy. I would hope this first one isn't bad. The 4 we drop down, and hopefully we recall that we took the derivative of secant to get a secant tangent. So this should just be a secant of t. And then this would have been 6t squared divided by 2, so that's a 3t squared, and then definitely 1r plus c. And then I don't know what it is, but when we start, instead of e of x, we put e of t, I start seeing a lot of this. So hopefully none of the 32 people in here do this, and I see this magical t appear in the denominator. Okay, that does not belong there. So erase that, right? We only divide by the coefficient of the variable, and the coefficient of t is a 1. So the antiderivative of e of t, or e to the t, is just e to the t. Just reproduces itself. You would divide by a 1, but we don't need to show that. From there, same as everything else we've been doing, take these two values, that our velocity is a 5, when our time is a 0, and then these, you have to recall some things. This is the reciprocal of cosine, so we would want to do whatever the cosine of 0 is, we want its reciprocal. Cosine of 0 is a 1, reciprocal of 1 is a 1, times a 4, so that just becomes a 4. Plus anything to the 0 power is a 1. And then plus our c, and then we see all that work, we get a c of 0. That is very rare, especially if I'm writing them, really for anybody, because what happens is, if it's a 0, if you forget your plus c, you would have gotten the right answer anyway, because now we pretty much just write this guy, and we now know that our c is 0. So it's pretty rare that that happens, just because then you still get rewarded if you forget your plus c. But in this case, there is no constant. When we get to the 3t squared, that is our final answer. All right. Now, 6 and 7, we pick up the difficulty slightly. Now the separating of the variables becomes pretty critical. The previous couple, like, it's not that big of a deal. Some of you are wondering, do I really need to show that I'm multiplying the dx over? But once you start dealing with these, where you also now have x's and y's on the same side, now that separating of the variables is pretty critical. So it's just simple algebra. You're going to multiply this dx over still. That doesn't change. But we certainly don't want that y intermixed with all those x's over there. So we want to move the y over at the same time. So just simple algebra, we would want to divide the y over. So we ultimately end up with this. Now our variables are separated. So that's why that first step, that in the first couple on the front page, it seems sort of trivial to multiply that over. But now when we start getting x's and y's on the right-hand side, now obviously you're going to have to do that. Now we do our antiderivative. The right-hand side should be very easy. You get 2x squared divided by 2, and then plus your c. See what you think on the left-hand side. All right, first time people see this, they think it's weird. We've never done this before. What am I supposed to do right here? Really, really common to see it written like this. So I'll show it the first time, and hopefully in the future you just don't have to rewrite it all the time. But isn't dy divided by y, wouldn't that be equivalent to a 1 over a y just multiplied by dy? Those are equivalent expressions, just written a little bit differently. Because once it's rewritten, this now better be familiar to us. What have we taken the derivative of to get a 1 over anything? Really, in this case, a 1 over y. Isn't that, although I'm going to have to move this down just a little bit. Isn't that a natural log? But in this case now, it is of y. All right, so whenever you see that, if you ever see, and you will, obviously, if you see like a dx over an x, if you want to rewrite it, feel free. It is a better visual. It's a little easier to see and recognize it, but this would just give us a natural log of x if you see that. All right, so then same thing we did on the front page. Go ahead and substitute in our values. So our y is a 1 when x is a 0, and then once again, although let's make sure we remember this. Keep all these in mind: natural log of 0, natural log of 1, natural log of e, natural log of e to a power. We need to know all of those. This is 6. The natural log of e is a 1. The natural log of 1 was what? Remember that one? Anybody here remember that one? Confidently remembers. That's our 0. The natural log of 0 is undefined. We can't do it. We can only do the natural log of positive numbers. So this is what we have here. So this is just a 0. So then we can go ahead and rewrite this. The natural log, the absolute value of y, is equal to x squared. Notice what I'm asking you to solve for, though. We want to figure out what y is. So to get rid of this, you're going to use your e to get rid of that natural log. Now we don't necessarily need that absolute value anymore, and all we are left with is that, e to the x squared. All right, makes sense, hopefully. All right, next one. Let's see where we're at, because this is really the last one. And I have the next question is an old AP question from a number of years ago. They don't make them quite as easy as number 8 nowadays. But 7 is the last kind of new problem that I came up with. So go through the first few steps. Give you a couple minutes. Separate your variables, do your antiderivative, see if you can figure out what your C is. The algebra is critically important here. These are really, really common free response questions. And if you separate your variables incorrectly in that very first step, they will not give you any partial credit beyond that point. They won't read along with you any further. I would consider this, your first day of doing these, a hard one. Like if you can get through this well, it's pretty good. I would definitely consider this the hardest one of the 7. You understand how we what we did here? Pretty similar. So you can think of it as if this is an over, and just divide by 1 squared. Or multiply by 1 over y squared. Cross cancel. 1 over y squared. Actually, one of the reasons are the algebra part of it. Yeah. Only get natural. This guy. Remember, we also also set up kind of products of two different things. We can't just do the antiderivative all the time. Yeah, there's a lot of different. Okay, let's see where we're at home. Not going so well here in class, so let's go through here. All right, first let's kind of keep it in the same order we would have done these before. We're going to multiply that dx over so that it ends up on the other side. Then this y squared on the right hand side is bad. We definitely do not want that. We want it on the left hand side. There's different ways to approach it. Since this is in the numerator, just think you're going to divide by y squared. Or if you want to think of it as multiplying by 1 over y squared so that that's going to cancel, that might be a better visual and easier to understand. So that what we ultimately end up with is a 1 over y squared, or some of you may have dy over y squared. I will say this is harder for people to recognize. It's a little bit easier to write it like this to see what's happening. And then on the other side, if this is now gone, right, we move that out, this would now be a 1 over x times your dx. So the algebra you need to be really, really careful with. That's one of the reasons a lot of people make a little mistake on this. The second mistake, I've kind of seen every little pitfall as I walked around the room. I saw all of them. Actually, it was actually quite perfect. The next thing that I saw, this is a natural log, the natural log absolute value of x, but we only get natural logs if it's 1 over x to the power of 1. If I had 1 over x to the power of 2, remember how we would bump that up and then just do the power rule? That's what we have going on over here. So let's bump this up, rewrite this as a y to a negative 2. So, oops, that. And then we just do our power rule. So add 1 to that power. So y to the negative 1. And then divide by that negative 1. And then another pitfall that I saw, we need to make sure that we remember our plus c when we do our antiderivative. So that has to be there. That's the whole point in you getting this information here. We're going to use that to figure out what our c is. I'm going to simplify this, so it's really a negative 1 over a y, and then that equals the natural log absolute value of x, and then plus our constant. Say that one more time.
What about the big one? Did you take the antiderivative?
This guy here?
Yeah.
Sort of. Where'd the dx go, CC? Didn't that also go away on the other side? Actually, I get this question a lot here. So like up here, this dy is no longer here anymore. This dx isn't there anymore. See, what? And I'm going to guess there's a lot of people, whether you voiced it or not, if you're here or at home, are wondering, it really pops up on the second page. Where's my, I have two screens working, I can't find my mouse. Where is it? Back. There, it's weird why it looks like that. Are wondering what's happening to the dx here. Oh, that's why. Yeah, kind of wondering what's happening to the dx, where did our dy go? But in every single problem up here, it's the product of these two. So it's kind of like saying, what's 2 times 3 equals 6? And asking, where did that 3 go? It's the product of these two that are giving us that 6. So when we did the problem the other day, you remember how I gave you y equals 2x? And then we use the area underneath here, which is our change in x. When I did 2x times the change in x, pen's not working. When we do that antiderivative of that, the product of these guys multiplied together, that area is what's giving us our antiderivative. So the product is giving us the antiderivative together. Something we'll do it later, I'll kind of show that a little bit better. But it basically, you can think it just drops out, sort of, okay? More than anything. All right, plug in your values now. So you let your x be a 1 when y is a 1/3. So I would get a -1 divided by 1/3. And then our x, natural log of x, which is a 1, plus your constants. All right, so -1 divided by 1/3 is a -3. I think this pen is on the fritz here. Natural log of 1 is a 0, so this c ends up being a -3. So then now we can write this equation. Create a little bit of space here. So here was our equation. And then now I know that my c is a -3. So I'm going to rewrite that over here. -1 over y goes in natural log absolute value of x minus a 3. We still got a little bit of algebra to do because we now need to solve for y. So I'm going to multiply both sides by y. So it looks like this, which would then mean pretty much we want to divide by the quantity. So you're going to get -1 over the natural log absolute value of x minus a 3. All right, that should be our final answer. So a lot of little things there to get through, a lot of little places to make a mistake. All right, where are we? 7 minutes. All right, any questions on that before we get to say? I want to do A and C in this AP question if we have the time. Yeah, Safian.
You can take up -1 over y.
Are you good? So we did this and this. Are you good through these 2 steps?
Not really, but
Okay.
y is a -1 over 3.
Do you know where that came from? Okay. So let's go back up to here. When we separated our variables, see how I had the 1 over y squared? So what we want to do this antiderivative, I want to take this and move it into the numerator to make it a negative power. So 1 over y squared is the same as y to a -2. Good with that? So now we do our antiderivative, and that's the power rule. So I want to add 1 to the power. So a -2 plus 1 gives me this power here. And then whatever that new power is, I've got to divide by it. So then I divide by that -2 plus 1, and that's where the -1 of the denominator comes from. And then we just rewrote this now so that we have this positive exponent again. Okay. All right. Any others? Anybody at home? Good. All right. Then the next one. So this, as you could probably see, is cut and pasted. So let me write this down. It's a pretty simple little guy, really. But the reason I like giving it is just to make sure we keep things straight. So A and C I want to get through. Because if you understand where we're at, you're given a velocity equation, or velocity with respect to time. Letter A is asking you for the acceleration. Letter C is going to ask you for the position. So that's why we got to keep our signs straight, keep our rules straight. So A should actually be very quick and easy. So do A, find the acceleration at any time. All right, that should take 10 seconds. Just remember our derivative rules. The derivative of a constant is 0, so the 1 would go away. The derivative of negative sign should be a negative cosine. So we should get initially a negative cosine. You leave the inside alone. And then we've got to do our chain rule. These are both the coefficients, so the derivative of 2 pi t should give you 2 pi. So that should have been our derivative / our acceleration. All right. Good. All right. Look to letter C then. Letter B, if we have time here in a minute, we might. I don't know if we will. But if we go to now letter C, I want you to find the position. So now we got to take our velocity equation that you were given to work with. And we've got to do the opposite of what we just did in part A. We want to figure out what our position is at the time of 0, 0. here's now where they can see your work. You better name this the correct function. They will take off a point for this. So the antiderivative of velocity is our position. If you look at your paper, the position function is named x of t. We do not want you then to be renaming their functions. What I mentioned earlier as well, when we do the antiderivative of 1, if you slip an x in there, that'll get marked wrong. Okay, we're dealing with the variable t. So the antiderivative of 1 should have been just a t. The antiderivative of negative sign should be a positive cosine of 2 pi t. In letter A, we had to multiply by that 2 pi. In an antiderivative, we would now be dividing by that 2 pi. And then we also now need our constant. From there, we want to figure out what our constant is. So I didn't write it, but x of 0 is 0. So that's telling us our x position is 0 at the time of 0. So let every variable become 0. So that should give us on the next step 0 equals 1 over 2 pi plus your constant. So kind of a weird constant in this case. It's a negative 1 over 2 pi. And then we can write our position at any time, which is the answer to the question, because we now know what our C is. All right, and then that's our guy. All right. Now, letter B we won't do, but just as a little refresher, it's not something we've had to talk about in a long time. But in letter B, if I ask you when is your particle changing directions, that is when our velocity equals 0. Your velocity was the equation that they gave you. This is a little trickier trig equation. Actually, we have 2 minutes because I'm not sure we could solve this if I told you to do this on your own right now, because you haven't done one of these in a while. So if you set that velocity equal to 0, we really want to solve this by isolating our trig equation when you solve this. So set that equal to a 1, add that sign of 2 pi t over. And then what we're now thinking, consider your unit circle. We're trying to figure out what angle right here has a sine value. So a y coordinate of what angle is a 1? Wouldn't that have to be up here at pi over 2? So what has to be true is this expression here, that 2 pi t, has to be equivalent to pi over 2. Pi's then would cancel. And then if you now divide by 2, wouldn't that give us a 1/4? However, there's also another answer. I'm trying to write an and. Crap. That's what I was afraid of. Maybe we'll do that tomorrow. It'll take 1 minute to figure out what that other point is. But that's it. Okay. You heard the bell. We'll see you guys tomorrow. All right. Have a good day. Yeah, no. Somebody say something.